almost everyone here, and we can start or continue. Right. It's being recorded. Yeah. Okay, so in the previous class, we finished discussing scattering, and started discussing circular orbits. Some information which can be easily obtained about the system, right? So we found an expression which can be used to find the amount of angular momentum that you have to provide to a system in order to have it on a circular orbit. Okay, I need to write that down because we will need that. So let me rewrite the previous class results. Okay, probably first I need to write again the topic, the title, the circular orbits. All right, so let me write again circular orbits. Right, and we got these two expressions. So from first one, f as a function of r naught equals to minus, wait, let me grab my notes. So it will be minus L squared over m r to the power of 3, r sub 0. R sub 0, it's a radius of a circular orbit. So, and from here, of course, you can get the value of L. And the second one, okay, let me write here in the line, E equals to, right, what? The value of the potential energy and plus that's centrifugal potential, right? Okay, so the first allows us to get the value of L, the second, the amount of total mechanical energy that the system must have in order to be on the circular orbit of radius r naught. All right, okay, so now, next, we need to get conditions which system has to satisfy in order to have a circular orbit, a stable circular orbit. Yeah, the key word stable circular orbit, right? And so now, yes, so what does it mean stable, right? So if you have a circular orbit, right, I couldn't find any other circle then except for this ring from the labs, right? All right, so if you disturb it slightly, so it will start oscillating somehow around circular orbit, but still it will be moving around the circular orbit, right? So it means stable. Of course, unstable if you disturb it slightly and the particle just fly away to somewhere without coming back, never coming back, right? So we need to get that. Right, so let me write, let's get criteria for a circular orbit to be stable. I will put a new small bullet and criteria for a circular orbit to be stable. Okay, underline, so because that's basically the the key. All right, so what do we have to do? We need to get an equation of motion, all right? And the one which I wrote in the previous class and from which we got this. So let me rewrite it. So that's mr double dot. Again, let me get my notes because I don't remember by heart. Mr to the power of 3 and equals f as a function of r, right? So that's the equation. But again, nothing wrong with this equation, of course, we all know, but what is not good about this equation for our goal, for what we want to get? The thing is, we want to disturb what? We want to disturb the, okay, an orbit, a circular orbit. But right now in this equation, we have what? We have the second derivative of r with respect to time. So if we start disturbing this equation, right, modeling the disturbance, physical disturbance, we basically are going to model sort of like a disturbance of disturbance of the history. But that's not what we want. We want to disturb the orbit. equation for an orbit. And of course, equation for an orbit, in order to get equation of an orbit, we need to change this equation slightly. We need to get rid of this derivative with respect to time and introduce a derivative with respect to theta. So if you solve that second order differential equation, you will get r as a function of theta, orbit, right? Because again, we want to disturb an orbit, not a history of the orbit, right? Okay, so let me write, I will probably put like this and open an explanation box. Right. Probably I will write this way. So we want to disturb the orbit, not the history, right? Yeah. Since we want to disturb an orbit. Okay, circular orbit, of course, but it's anyway some circular orbit, but not a history. But not a history, right? Okay, history, just a smiley face, right? So we want to rewrite this equation. And also, since we're going to go eventually through some mathematical manipulations, and whenever you work with equation like this, no, whenever you have to get through mathematical, through calculus, dealing with this equation, it's better to change from r to 1 over u. Dealing with u in this equation more convenient, right? Of course, at the end of the day, of course, every time you will have to go into the expressions in terms of r. But in order to get through this painful mathematical manipulations, it's better to switch every time from r to u, where r equals reciprocal of u. Okay, so now let me introduce u equals 1 over r, right? So we need to do this, replaced. And also, as I said, instead of this derivative, right, instead of r double dot, which is second derivative of r with respect to t, we need to introduce u double prime. And that smiley face in my way, so let me remove it. Enough of smiling. Right. Second derivative of u with respect to theta. We've done it in an undergraduate level course. It's just like a 5 minutes of it's 5 minutes of calculus, so I'm not going to do it. Right. We've done it on an undergraduate level course, or you can do it by yourself. Reasonably straightforward. Right. So as a result, we will get this equation. Right. So it will be u double prime. Again, u double prime, it's a derivative with respect to theta now. So if you solve this equation, of course, you will get immediately an orbit. Right, u double prime plus u equals to what? Minus m L squared u to the power of 2, and function which describes force, but of course it's a function of u. All right, we replaced r. Okay, this double prime almost blending. Let me. Okay, double prime. Now it looks better. Okay, so that's the equation. Okay, you know what? Blue will be better. So, which we need to disturb, right? Introduce small displacement to u plus epsilon, and then see what we can get out of this. But before we do that, let me introduce just for a second. Okay, not for a second, for 10 minutes, right? New function g. Whatever we have here on the right-hand side, let's call it g function, right? Because it will make our calculations a little bit easier, right? It's not a big deal, but I found it useful. So let's denote g as a function of u. It's this minus m L squared u squared and f as a function of u. It will help to get through calculus. And before we start again disturbing the equation, disturbing the orbit, let's calculate the value of g at the circular orbit, where u equals to u naught, right? All right, so Yeah, and of course, let me write. So u naught, it's a 1 over r naught, right? And r naught, it's a radius of a circular orbit. Right, so let me calculate sort of like a preparing ingredient, which I will need later in a few spots. G at u naught, it will be equal to minus m L squared and u to the power of 2 and f at u naught. Okay, so value of force at the orbit. That's why from the very beginning I told you I would need that. So that's what I wrote it here. But of course it will be, instead of r, we have to use u, right? So from there, right, it will be minus m L squared u to the power of 2 and minus L squared. This r to the power of 3 will go to upstairs u to the power of 3. And divided by m. All right. Okay, m goes, L squared goes, 2u also go. As a result, we're getting just the value of u. All right. So that's the value of the function g at u sub 0. Okay, so now we will need it later, and now let's disturb the equation. Now I will put a small bullet. So now let's disturb. Okay, now let's say we decided to use orbit r naught, so let's disturb the orbit. And of course, the equation. So we model that disturbance by disturbing the equation. And so u, it's a u naught plus epsilon. Of course, epsilon is a small value, small disturbance, right? Of course. Okay, you know what? Let me sort of frame it a little bit, so to find it easier. Right. Okay, so now let's plug it into the equation. Right. So of course, it will be u naught plus epsilon double prime plus u naught plus epsilon equals to minus m L squared u sub 0 to the power of 2. Yeah, yeah, you know what? I already introduced g. Since epsilon is small, of course, this, which is g, okay, let me, so of course, this is g. Of course, we can use just Taylor expansion. So let's just expand function g in terms of u. Right? I mean, not u, epsilon. Epsilon is small, right? So as a result, we will get, so first the value of g at u sub 0, right? Taylor expansion, then plus epsilon and the first derivative of g. First derivative of g, of course, at u naught, and then plus 1 over 2 epsilon to the power of 2 and g double prime u naught, and of course plus and so on. On the left hand side, we have first power of epsilon, first order terms. It means that this the third term on the right hand side, we can dump it. It's too small, right? So this will be too small, so we can neglect it. And as a result, also this g at u naught we just found, it's u sub 0, right? As a result, this u sub 0 and this gets cancelled, and so that will be dropped. So now we just need to combine these two terms. I will just move this term to that side with minus, right? And of course this is constant, so we will end up just with epsilon double prime, and then plus, probably I will write with plus, so it will be 1 minus g prime at u sub 0 epsilon and equals to 0. So that's what we're getting, right? Yeah, of course. And of course, at this point, you can start screaming kind of, wow, we're getting simple harmonic motion. But we need to come down and carefully look at this, right? So first of all, let me denote. Let's denote. Makes sense. All that construction denote beta squared as 1 minus g prime at u sub 0. Again, probably it's worth of framing because I will need it several times in the future, right? And as a result, of course, we can rewrite this equation, right? And again, careful because depending on the value of beta squared, this equation can give us oscillations or a runaway solution, right? So in order to have oscillations, in order to have simple harmonic motion, beta squared must be positive in this case, must be positive, right? Or if you move to that side, of course, will be minus in front, and anyway, beta squared must be negative, right? Okay, so I can write as a result like this. So oscillations are possible. Basically, we're going to have simple harmonic motion, right? When beta squared is larger than 0. Beta squared is positive, right? So it means that when beta squared is positive, we will have stable circular orbit. Okay, yes, stable circular orbit. Or it's better to say stable near circular orbit because we already disturbed it. Right, so stable near circular orbit. So, okay, so let's write down the solution probably, right? And then, since inside of beta squared we still have this g prime, we need to reveal all that information. Right now we just cover it with a nice cover, right? Called it beta squared, but still inside of that there are plenty of hidden information, right? But anyway, so let's write down the solution. So solution will be epsilon will be equal to, okay, we're going to use what is called again phase shifted cosine solution. At least that's how we call it in undergraduate level course, right? So it's a amplitude times cosine, and usually it's a omega t minus delta, but in this case, instead of omega, we have beta. So it will be beta, and instead of t, because now it's not a derivative with respect to time, but a derivative with respect to theta, so it must be b theta. And then usually we have initial phase minus delta, but that initial phase is just initial angle, right? Because variable is theta. So of course, every time we can slightly adjust our coordinate system, right, by turning it slightly by some angle. And that constant can be, we can make that constant 0. So let's assume that we already turned our coordinate system and that initial phase is 0, right? So delta equals 0 initial phase. Every time we can easily do that. Right. Okay, so that's the solution for epsilon, but of course we're dealing with u. So of course we can write u, and that's, of course we can write u equals, of course u as a function of theta equals to u naught plus a cosine of beta theta. Right. So that's the solution. It's worth of framing, right? So of course this gives us a circular orbit, and then this is a disturbance, basically oscillations around a circular orbit. So now, yeah, let's dive inside of beta squared. Okay, probably I will move to this side. Let me estimate. Beta squared is over there. Yeah, probably I'll move to that side. Yeah. So now, okay, let me write. So back 2 beta to the power of 2. Okay, and now I will continue here. So we need to take the first derivative of g, of course, right? So it will be g prime at u sub 0. All right, this. And where is my g? And again, prime, it's a derivative with respect to u in this case, right? So where is my g? Here. No, it's a g at u. Here. So it will be d over du. And actually, I was planning to circle it over there, but by mistake, I circled this part. But anyway, it's not wrong, right? It's absolutely correct. But my intention was to circle it over there. So minus m, what, l squared, u squared, and f as a function of u. Right? And again, it's not a derivative with respect to theta. It's a derivative with respect to u because we're expanding it over here, right? Taylor expansion. It's not this. Okay, so now let's, so it will be, first we need to differentiate with respect to that. We will get minus 2, and that minus give us plus, so it will be 2m, then l squared u to the power of 3, and also at u naught, right? So first we need to differentiate, and then of course plug u naught instead of u. Right, so it will be the result over here, u naught to the power of 3 and f at u naught. Okay, so now we need to differentiate with respect to that. So it will be minus m l squared u to the power of 2. Again, u naught immediately. I replaced u with u naught. And the derivative of f df over du, and of course at u naught. Okay. Out of this mess, we need to extract something which should look better. In order to do that, let me multiply this by f at u sub 0 and divide it by f u sub 0. Okay, so now again, let's recall the value of f. It's a force, you remember? It's a force acting and giving a circular orbit at the orbit. So that's why I wrote it from the very beginning. So it will be minus, okay, let me write it here like this. So this is what minus l squared u naught to the power of 3. No, to the power of 3. Right. Now I started doubting myself. No, everything is good. And divided by m. And then what else? This m l squared, where's my g? Again, g is here, so it's a minus m l squared u to the power of 2. And this f, okay, all this, okay, let me use blue. This construction, like this, right? Oops. It's just the value of g at u naught, function g at u naught. So you see, g minus m l squared u to the power of 2 and function f. So it's a value of g at u naught, which is u sub 0. Right? So I can write that this is g at u sub 0. And of course, u sub 0 equals to g at u sub 0 equals to u naught. And that's why I spent prepared this ingredient before the class, before I started messing up. All right, so now this l squared goes, u to the power of 3 goes, m goes, well, we have just 2. Awesome. 2, okay, it's equal, right? Then out of this mass, so plus will appear. Here we have u sub 0. Yeah, that's it. So just plus u sub 0 and then f at u sub 0, and the derivative of f with respect to u at u sub u naught, right? Of course, here it's a product. So that's the value of g prime. And now go back to beta squared. So now we just mix with this one. So it will be beta squared equals minus 1 minus g prime at u sub 0, right? So if we subtract, you will get something is fishy, something sooner or later, of course, you will start telling me, where's your minus, right? This minus, I forgot to write it in front of that 2, right? You see, this is equal to negative value, so all this gets cancelled, but minus stayed. Right, so that's why I'm looking now. It looks not right, so minus 2. Okay, minus 2. Now it looks correct, yeah. Okay, so now, yes, everything is correct. So minus minus give us plus, so we'll have 3 and minus this construction, right? Yeah, of course. U sub 0, f at u naught, and this derivative. Whew. Getting closer. So pretty much, yeah, it's a beta squared, which is supposed to be, where is my beta squared positive? Okay, you know what? I should have framed this with red, because now I'm running with my eyes over the board in an attempt to find it. So, and that, of course, beta, that expression must be positive. But it's not over, because at the end of the day, every time we usually have force as a function of r, we usually go into this variable u in an attempt to simplify our calculations, in order to simplify life in calculus. But of course, at the end of the day, we need to go back to r. Right? And again, we want two conditions. We want a condition written in terms of r, not in terms of u. So let's go back to r. Right? Right? So now back to r, right? Of course, which is 1 over u. Okay, so you know what? Probably I first change that derivative df over du. Right? df over du at u naught, so it will be df over dr and dr over du, of course, at yeah, u naught or r naught. And dr over du, okay, let me write first df over dr at r naught, and this will be minus 1 over r naught to the power of 2, right? dr over du, hold it. No, dr over du. Okay, trying to skip steps. Dr over du, I'm differentiating first. I will get minus, okay, u squared, all right, u naught squared. And then, of course, it will give us r to the power of 2 upstairs. Okay, that's why I'm afraid sometimes skip steps to make silly mistakes. So it will be equal to minus r naught to the power of 2 df over dr at r naught. Okay, so that's correct. Yeah. So that will help us to replace that. And so now back to beta squared. So it will be 3 minus, instead of u naught, it's a 1 over r naught. Then, okay, next to that will be, all right, let me increase this size of this. It's a f at r sub 0. And then instead of that will be minus r squared and df over dr at r sub 0. Okay, 1 r will be cancelled. Minuses give us plus. So we'll get 3 plus r will be upstairs. R sub 0 divided by f at r sub 0. And derivative of our force evaluated with respect to r, evaluated at the circular orbit. Okay, so that's the condition. Again, let me check if I got to the right place. Yeah. So now let me just rewrite it, frame it, and we'll start. We will start using it soon, but not immediately. So it will be beta squared equals to 3 plus r naught function, the value of the force at r naught, and df over dr at r naught, and framed it. Yeah, and of course beta squared must be positive, right? Okay, I should add this. Right. And now all that must be framed. Right. So condition for circular orbit to be stable, right? So what you need to know, just the expression for the force, Coulomb force, gravitational force, spring force, whatever force you have, you cover potential or get the force, calculate beta squared if it's positive, okay? All right, so circular orbit will be stable, right? Circular orbit for that particular force will be stable, right? And of course, L and E, the values of L and E you can get from these equations, right? In order to get a circular orbit with a particular R naught, it can be 5 meters, 10 meters, so of course values of L and E going to be different, right? Okay, yeah, and of course, yeah, the solution is here, so I'm not going to rewrite it one more time. Okay, so now we have conditions for an orbit to be stable, but what about closeness, right? I mean, if you disturb it, if you disturb a circular orbit, right? Under which conditions you're going to get a closed orbit? It means that if, for example, it started at this point and after maybe one circle or maybe two circles, under which conditions it will come back to exactly the same position, right? Are we going to get closed orbit, and under which conditions closed orbits are possible, right? So now it's the second part. And okay, I use blue, so now let me continue using blue. So now it's the second bullet. So this is the first one, now the second one. And the question is, when is near circular orbit closed? When is a near circular orbit closed? And the question mark, right? So first I will write the condition, and then yeah, we will sort of massage it, right, and start looking at examples, right? And it's again about this beta. So here we need to analyze this beta in order to get information if this circuit, if the orbit is stable or not, and then in order to get to come up with the conclusion if your orbit, disturbed orbit, going to be closed or not, again you need to look at beta, and I will write so when beta, so here it's a beta squared, here we have beta, so square root of that. So if beta is a rational number, a rational, not irrational, right? If beta is a rational number, a rational number, basically rational means it can be written as the ratio of two integers, right? Rational number, ratio of two integers. Okay, then after, okay, all right, now after, I will just say, and then of course we will show, right? After P oscillations in R, like, okay, I don't have a picture, right? So for example, from R minimum to R maximum back to R minimum, after P oscillations in R, radius vector will make Q complete revolutions in theta, and orbit will be closed. Right now it sounds very confusing. Let me get to the examples, and of course I will write what I just told you, right? And it will get clearer when I draw a nice picture. Okay, I hope it will be a nice picture. But for now, yeah, it sounds confusing. After P oscillations in R, what it means, okay, it needs to be shown on the diagram, right? Radius vector will make Q complete revolutions, and after that orbit will be closed if beta equals to, can be written as P over Q, right? And of course P is an integer, Q is an integer, right? Okay, so again, as I said, I will write what I just told you in a second. Okay, not as in a second, in a couple of minutes. All right, so now we know the solution, all right? And let's write the condition when condition for one cycle in R or one cycle in U, because U and R basically right, reciprocal of each other, right? So I can write like this. So U at theta, and as I said, yeah, condition for one cycle in R, one revolution in R. So so it means, this equation means that after angle of delta theta, again, I will draw the picture in the example. After angle of delta theta, U or R makes makes one oscillation, right? The value of R reproduces itself, the value of U reproduces itself, right? So that's what we have. After angle of delta theta, right? You make system moves by angle delta theta, and R will go, for example, from R maximum to R minimum and then back to R maximum. Right? So, and let's write this explicitly. Let's write this explicitly since we have solution. So I can write U sub 0 plus A cosine of beta theta. So the left-hand side, right-hand side, of course, will be beta theta plus d theta plus A cosine beta theta plus delta theta. Of course, it can be correct. This can be correct only when beta times delta theta equals to 2 pi, right? Because cosine is a periodic function, period is 2 pi. So if this times this equals to 2 pi, it will be equal. Okay, I expect your questions, right? So just a second, I will write this. So it's true when beta times delta theta equals to pi. Of course, you can start screaming. Come on, it's not absolutely correct, because it can be equal to pi times some kind of integer times 2 pi n. I know that. That integer will appear from this beta. Beta is P over Q, right? So that integer will come from beta, right? So that's why I'm not adding that integer over there. Not adding that integer next to 2 pi, all right? And so of course it will be P over Q times delta theta equals 2 pi, and of course P times delta theta equals to Q times 2 pi. Okay, so that's what we're getting. And again, it's still not completely clear. I need to draw a picture in order to make this condition clearer, in order to make this condition clearer. But it means what? After P oscillations in R, again, I will write it, so don't try to write from my words. After P oscillations in R, radius vector makes q complete circles and orbit is it reproduces itself, right? It comes back to exactly the same point. Okay, so let me write that in better words using my notes. So after p cycles in R, the radius vector will make q complete revolutions and occupy its original position. So of course it should be written, right? Let me frame this first. And then again, before we start looking at the example, it will be confusing, right? So it means that after p cycles of R, or p revolutions or oscillations in R, the radius vector R will make q complete revolutions in theta. Radius vector R will make q complete revolutions in theta. And occupy its original position. Its original position. So this statement written in words. And now let's look at the example. After this example, it will become very clear. Okay, let me see what I need. I think I don't need all of this anymore. And I can safely erase it all. Safely for future calculations. No, I don't need anything of this. Okay, example. All right. Example. Let's say, what if p equals 5 and q equals 1? What if p equals, for example, 5 and q equals 1? So it should be like after 5 cycles in R or 5 oscillations in R, radius vector will make 1 complete revolution and the orbit will be reproduced. Yeah, will get closed, right? So let me draw the picture. Probably I will draw it somewhere in the middle. All right, you know what, let me use green for coordinate system. All right, so let's say this is, all right, right, and I need a nice circle, and I'm using plates, right? And I've been using it so much, it's completely dirty with markers, but I cannot find anything better than this, right? Yeah, it's better to have a little bigger than this, right? Okay, I will try to squeeze. Homemade art using plates, right? Okay, all right, so let's start, for example, from this point. Let's say this is, okay, let me use a red for an orbit. All right, so let's say initial position of a particle is over here, and this is maximum, R max, right? Then first it will go to minimum and then back to maximum, let's say somewhere up here, right? So let me draw it. So first it goes to minimum and then back to maximum, right? So this is, of course, R max. This is R min. And this delta theta, which I used here, and I told you that's the angle over which R makes one oscillation, one cycle. This is angle. Okay, let me also draw this. This angle is delta theta. So you see, our maximum, then minimum, and back to maximum. So we have one revolution or one oscillation in R, from R max to R min, and then back to R max. And angle delta theta. All right. So that's what delta theta shows, gives us, right? Then, of course, I can write that this, for example, it's a u at theta naught, but theta naught is 0, right? And plus, oh, you just theta naught. Plus will be later. All right. Okay, now, then second cycle in R. Let's say it will be here. No, it's a maximum, then it will get minimum here and maximum somewhere up there. It's enough? It should be enough, right? All right, let's say here will be again our maximum. So here will be minimum. So again, it will go to minimum, then back to maximum. Okay, it's not very smooth. Right. Okay, so this is our next delta theta, right, which gives us an angle over which R reproduces itself, makes one oscillation, right? So again, this is delta theta. And again, it's a R max, between them is R min, right? Okay, it's a really distorted picture. Right. Okay, so we have two oscillations in R, but still orbit is not closed, right? And according to this, we should be able to make 5 oscillations in R like this, and our radius vector should be able to make one complete oscillation in theta. One complete circle, right? So now let's continue. So again, let's assume this will be somewhere here minimum, and then again maximum. So it will be something like this. Right. So this will be again delta theta, next one. Right. And okay, now let me move a little bit faster. So it's a 1, 2, 3 will be 4 over here somewhere, approximately. Right. Again, it will go to minimum, back to maximum, and then here somewhere will be again minimum and maximum. Okay, sorry, picture is distorted. It's called modern art. It's not a distorted picture. Right. You just need to change your understanding of pictures, right? So this will be again R max, and of course angles, right? So it will be delta theta, and since it's colorful, it should be easily it should be very solvable, right? Should be easily can be easily solved. All right. Okay. What else I wanted to say? Something else I was. Yeah. So of course this will be what? A u. So here it's u at theta naught. Here theta naught plus 1 delta theta. Of course theta naught is 0 over here, obvious, right? Right. So here it will plus delta theta. This will be, of course, u at theta naught plus 2, of course, plus 2 delta theta. This will be u at theta naught plus 3 delta theta, and this will be u at theta naught plus 4. And again, we come back to exactly the same position. So it's a u at theta naught plus 5 delta theta. Delta theta. So this point at theta naught and theta naught plus 5 delta theta, it's the same point. So orbit is closed. And that's what I told you, right? So after 5 oscillations in R min, R max, R min, R max, R min, R max, 5 oscillations in R, radius vector makes one complete revolution in theta, and orbit is closed. Right. So that's what these numbers means, P and Q, number of oscillations in R and number of complete revolutions. 2 pi, no, 4 pi. Sometimes you can, in this case, one complete revolution was enough. Sometimes we will see an example. You have to make 2 complete revolutions in order to close the orbit. It depends, of course, on the force. It all depends on the force. It all depends on beta. First, you calculate beta squared to get information about if your circular orbit stable. Then you massage it deeper. Okay, take a square root. And if it's a rational number, then, of course, the orbit can be closed. Right. Okay, so now let's look at a bunch of examples. Now we will draw more pictures like this, but they will be smaller. So let's look at force which proportional to the r to the power of n. Okay, so pretty much we've done with calculations. Now we just need to apply these results for several forces. And of course, one of them will be gravitational force, one of them will be spring force, and then some other forces which I cannot identify. Just practice that without actually knowing what's the nature of that force. All right. Okay, I will put probably a new blue bullet. So now it's just an application, right? So let's investigate cases. So let's investigate a few cases. Oops. All right. Where f, okay, let me write. So f equals to, okay, f is a function of r. It's not a good idea to write just f. It will be minus, again, you remember I erased over here, but minus is important. The force must be an attractive force, right? In order to have a circular orbit. If force is repulsive, obviously it's not possible, right? And we saw it at the beginning of today's class and at the end of the previous one. So minus which function, k, parameter k, and r to the power of n. So this, right? Okay, so we just need to calculate beta. So we just need to drag this force through this condition, right, to get beta squared and then beta and so on. But first in general, and then we will start looking at particular n. So beta squared, it's 3 plus r naught divided by f. You know what, let me rewrite first that condition, and then I will start applying it. Okay. So 3 plus r naught, then value of the force, it will be minus k r to the power of n, right? And then derivative. Derivative will give us again minus k times n and r naught to the power of n minus 1. N minus 1. Right. Okay, so simple things. K goes, minus goes. We will get r sub 0 downstairs and r sub 0 upstairs, so that will disappear, and as a result we will get 3 plus n. 3 plus n only left. 3 plus n, and of course this 3 plus n must be positive for a circular orbit to be stable, right? Of course, if n is larger, so now if n is larger than negative 3, then it gives us a stable circular orbit. Stable circular orbit. Okay, orbits, let's say, for different forces. And of course, you can have tons of circular orbits with different radii. Right. Okay, so now let's start at looking at particular n. N equals -2, n equals something else, right? I don't remember all of these forces. Let's start with n -2, right? First, gravitational force, gravity. All right, so n, of course, equals to -2. N equals to -2. And of course, force, let me write anyway, force is a function of r equals -k r to the power of 2. All right. Okay, so beta squared we already pretty much calculated. If you want, you can go through that condition again. I will just use it to recycle this, right? So of course, beta squared will be equal 3 plus n, so it's a 3 minus 2, right? Yeah, n equals -2, so it's a 1. So 1, of course, is larger than 0. Of course, the orbit, circular orbit, stable, right? Well, of course, we knew because from the very beginning, because what? -2 is larger than -3, so according to this, of course, should be stable, right? So, but anyway, I'm just again enjoying the results, basically it's called, right? So beta squared is 1, larger than 0, so it's stable. But now, what about closeness? So what's the p and what's the q in order to close an orbit, right? So now, again, now it's a beta. Here we had beta squared, now it's a beta. So beta equals 1, and of course, it's a rational number. We can write it as 1 over 1, right? So p equals 1, q equals 1. And now let's draw the picture. So p equals 1, right? Q equals 1. And now let's exercise my modern art again, right? You will get sick and tired of my modern art within next 15 minutes, right? Okay, so let me use blue color for the undisturbed circular orbit and red disturbed, right? Red. Right. Oops. Again, it's my container, takeout container. I don't remember when I get it. I think it's from one of the Indian restaurants. Right. So undisturbed orbit, right? So this is center. Okay, and let me emphasize. So this is which way I wrote? I think unperturbed. Okay, so it's a circular unperturbed orbit. Okay, circular unperturbed orbit. And all right, so what we have now in order to draw a perturbed orbit, disturbed orbit, so what? P gives us number of oscillations in R. So after one oscillation in R, radius vector will make one complete revolution in theta and orbit must be closed. So it means that if we start, for example, over here from R min, it's a minimum, it will go to, okay, yeah, you see my modern art is coming back, right? It goes to R max. Okay, let me show that this is R minimum. This will be R maximum. All right, it's a half a cycle. And then we go back to, again, R minimum, right? Sort of like a shifted, right, slightly, but of course it's not shifted, right? It's disturbed, right? So it comes from R min to R max and back to R min, right? So that's the disturbed orbit in the gravitational case. Disturbed circular orbit, disturbed circular orbit. All right, and probably I should label this. So this is nearly circular perturbed orbit. Nearly circular perturbed orbit. Okay, since it's a first picture, just to emphasize that red is a disturbed orbit, blue not disturbed. So next will be spring potential. We'll just look at a few. Okay, this condition I rewrote, so I think I should be fine, right, with erasing it all. So spring, all right. Spring force. Of course, n equals to 1 now, of course, right? So force, I can, which way I wrote it? F equals to minus kr, three-dimensional potential, of course. I mean, the three-dimensional force. And so in this case, n equals to 1. And of course, it will be stable, right? Because n is obviously 1 is obviously larger than -3. But anyway, so beta squared will be equal to what, 3 plus n, so 3 plus 1, so it's a 4, right? And of course we can write b as it will be 2 over 1. Of course you can say why not 4 over 2. Okay, you will just reproduce exactly the same speculations just twice instead of 1, right? So what's the point, right? So of course you need to take the smallest numbers, ratio of two smallest numbers, the smallest integers. Right, so it means that P equals 2 and Q equals 1. So after 2 oscillations in R, radius vector will make 1 complete revolution and orbit will be closed. So let's draw this. And where's my container? So, oops. So that's undisturbed, right? Circular orbit, of course, center is somewhere here. Yeah, give or take. And then, yeah, we have it. You have to make within one circle 2 complete oscillations in R. Okay, so let's start with R max. So let's say this is R max. Then it should go to min. Probably this will be minimum, and then back to maximum somewhere up there. Okay, it's a first cycle in R. And then, of course, it should go back to R min over here, right? And back to the original, right? So again, R max. So we have 2 cycles in R and 1 complete revolution. And orbit is closed. So you can ask me, I remember in the past some students asked me, so is it an ellipse? Maybe by accident. Ellipse, it's a well-defined curve, right? So distance from the point on the curve, distance from the one focal point to the point on the curve, right? And then the distance to the second focal point, right? So if you add those distances, it must be a constant number. Right? So ellipse, it's a well-defined curve. This is a disturbed circle. Maybe by accident it can be an ellipse, right? But I will never bet my money on that, right? It's just a disturbed circle, which kind of in a shape resembles an ellipse, right? Maybe, but most likely it will be just a disturbed circle, which disturbed in this way. All right. Okay, so now let's make the situation more complicated. So here we had 1 oscillation in R. Here we had 2 oscillations in R in 1 complete revolution. Now let's make 3 oscillations in R to complete 1 revolution. So now the next force, all right, okay, R to the power of 6. All right, again, now I don't know the nature of this force. All right, no way. I have no idea what's the name of this force. So I'll just write the expression. So it will be F as a function of r equals to minus k and r to the power of 6. R to the power of 6. So of course now beta squared equals to what? Of course it will be 3 plus n, 9, right? 3 plus 6, 9, of course positive, so it's stable, and of course beta will be equal to 3 over 1, so p equals 3 and q equals 1. Okay, so let me now draw quickly this situation. Okay, this is true art. Smear it on one side. All right, and so now again let's start with for example here max. Right, then there will be minimum somewhere here, then again maximum, then again here minimum, then again maximum. So it will be something like this. Right. It's sort of like a triangle around it triangle, right? So again, this is maximum, R max, again R max, and again R max. So we see, you see we have 3 oscillations in R, and we can make only one and one complete revolution, right? And orbit is closed, right? Okay, now enough increasing number of oscillations in R. Let's make situation slightly more complicated. And again, the nature of this force, no way. Right. Okay, I will write slightly lower. Right, so the force looks like this. So F as a function of r equals minus, and you see all these forces are negative, right? So minus, 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 right? Because all these forces must be forces of attraction. So it's minus k divided by r to the power of 11 over 4. That's the power, r to the power 11 over 4. Right. So in this case, n, of course, n equals to minus 11 over 4. Wow, that's nice. So beta squared equals, of course, 3 minus 11 over 4. So it's a 12 over 4 minus 11 over 4. It's a quarter, 1 over 4. Anyway, it's positive, so of course it's stable. Circular orbit, but we need to get beta. Of course, beta will be equal to 1 over 2. So now Q is larger than P, right? So now P is 1, P is 1, and Q is 2. So now drawing is a little bit more, will be a little bit more complicated, right? Again, I will start with undisturbed. Right. And again, this is the center, approximately. And again, let's start with R maximum. Sort of, it's a tradition, right? So R max, so outside of the circle. And so first it will go to, so first it's outside of the circle, then goes inside of the circle. Let me make it a little bit deeper. Right. So R max, okay, let me write it. R max, and this is R min. And so you see we've made only half a cycle, R max to R min, right? And we already completed half of a revolution. So now we will go, wait. It's not R min, it's not R min, it's not yet. More, we will go even deeper. Ah, damn it, right, so I need to, I should have looked, right, so, okay. No, it's wrong. All right. So it does like this. So first it goes, okay, this, because I started looking at it, I'm not getting 2 cycles in R, right? So it goes to this point, and only now it goes in the circle. And so only now it goes in, and only now it's R min. So now this is R minimum. So we've made only half a cycle in R, right? And we've already made one complete oscillations in theta. Okay? So now let's continue. So now it will start sort of unwinding, going back. So now it should go, okay, it should go back to this point, back to this point, and then goes outside of the circle. Something like this. Right. So first comes to this point, gets inside, then when makes one circle inside and then gets outside. So what we have? 2 complete circles and only 1 oscillation in R. So we started from R max. This is some kind of intermediate point. R minimum is only here. So this is half a cycle, and then again back to R maximum. So it's a 1 complete cycle in R and 1 complete revolution. I mean, two revolutions, right? So now it's more complicated, right? First I even started drawing in the wrong way, right? Okay, so enough of these examples, right? So now, in order to conclude this, of course, there are infinite number of closed near circular orbits, right? But the question is, are they truly closed? You can say, what, we've been drawing all this mess, and now you're telling that all this nonsense, right? Okay, the thing is, okay, now I realize why I needed what I just erased. But you have in your notes, right? Not completely. So all this closeness is to some extent approximately. They're approximately closed, right? Why? Because when we were deriving this beta squared, right, and then beta, you remember when we started disturbing our equation for u, right? And you remember on the right-hand side we had that function g, and we used Taylor expansion for that function, right? And we dropped the terms proportional to e to the power of 2. So pretty much it means that these results are approximate. So if you create a small disturbance, then very small, very small disturbance, then this is most likely will be correct, or reasonably correct. But if your disturbance will be slightly bigger, then you will start noticing something, orbits which are not completely closed, right? So pretty much, yeah, all this closeness are approximate, except, and Bertrand proved, right, we're not going to do it. So all these closeness are approximate except for 2 forces. The first 2 forces, gravitational force and spring force, gives us a true closed orbits. The rest, all these are approximate. So that's, again, we're not going to prove it. Probably I will just write it down, and we will call, and we will finish this chapter, right? Actually, I thought about moving slightly deeper, right? Okay, let me write a few words about this closeness. Okay, I will put a new bullet and write. So these orbits are closed only approximately. Which way I wrote? Okay. Closed only approximately. Oops. Approximately. And I will remind you that G double prime epsilon squared times G double prime, just to remind you, because of that term, right, that expansion. Right, and of course, yeah, as I said, if epsilon is very small, then it's good, but if your disturbance is getting larger, then of course you will see more and more they are open, right? Okay, so then Bertrand. Okay, let me spell it, his name correct, last name, Bertrand. Whenever I hear this name Bertrand, and it reminds me Agatha Christie story, all right, Bertrand's Hotel. Bertrand proved that the only n values that lead to exactly closed orbits are force of gravity and of course electric force, right, or any forces of that type, right. Proved that, let me just rewrite from my notes this, that the only n values that lead to exactly closed orbits of course we're talking about circular orbits only. For any initial conditions, right, pretty much disturbance wouldn't change. For any, right, initial conditions are, okay, all right, n equals -2. So first, n equals to -2, which gives us forces like force of gravity, electric force, right? Of course, electric force only attractive one, right? Because yeah, we can have repulsive, and of course, repulsive force will never give us a circular orbit. We showed it at the very beginning. So it will be -k over r to the power of 2, right? And spring force n equals 1, so F equals to -kr. So two-dimensional Hooke's force, right? Okay, so that's Bertrand's theorem, right? And enough of central forces. So from the next class, we will get back to the Hamilton's principle. Basically, we will start making a transition from the Lagrangian formalism to the Hamiltonian formalism. Right? Compare them, of course, get Hamilton's equations, and then we will be there for quite some time. Then we will start, first we will develop Hamiltonian formalism, and then we'll start searching for simplifications, right? Because you can choose different coordinates. In some coordinates, solutions can be easy, in some coordinates more difficult, right? So we'll start searching for easy life, right? And then for the place where the life is the easiest, right? So we will develop canonical transformations and so on and so forth, right? So there will be some long stretch of time where we're going to talk about only Hamiltonian formalism. Okay, guys, so that's it for today. And if you have questions, you can ask, right? And I will stay here and enjoy my modern art. At least it's colorful, right? Ugly but colorful.